Our today's guest is Professor Dr. Dame Jocelyn Bell Burnell, who was responsible for the discovery of pulsars while she was a radio astronomy graduate student in Cambridge. And subsequently, she worked in gamma ray astronomy, X-ray astronomy, infrared and millimeter wavelengths astronomy. Professor Bell Burnell's story has been both an inspiration and motivation for many female scientists across the globe. I'm very honored that you agreed to be our tonight's guest. Welcome. Thank you very much. It's really great to have you here.
Thank you very much. Am I heard okay?
Yeah.
Okay. So I wanted to say a little bit about transient astronomy, stars or things that flare up and die, particularly at radio wavelengths, because that's where a lot of the interest has been just recently. Although there's activity at many wavelengths, because this time domain astronomy is one that's developing very, very fast and will develop even faster when the Rubin telescope gets going. So I'm going to be talking mainly about the radio part of the spectrum. There is activity in other parts, undoubtedly, but in 20 minutes I can't cover the whole spectrum, so I'm going to focus on the radio astronomy bit of the spectrum. And this is related to the pulsar work that I was involved in 50 years ago. It's a development from this, a development noticed and driven by pulsar astronomers. So pulsar astronomers are watching how the signal from a star up in the sky comes and goes, how the radio signal comes and goes. And one of the things that they learned about was dispersion. Now, dispersion in radio astronomy is quite sophisticated, so I thought I'd start with dispersion in optics and optical astronomy. And you perhaps know that if you shine a beam of light through a prism or through a raindrop, you get this lovely spread of colors. The full rainbow, the spectrum of light. Something similar happens with radio waves. You get the spectrum spread out. And I'm going to illustrate it with this diagram, which has nothing to do with astronomy, but is a terrestrial effect. Early radio amateurs heard a number of curious clicks and whistles and things on their headsets when they were trying to pick up Morse code from a colleague or whatever. And this is a plot of frequency against time, and it's one of the samples of what you might hear. And there's two events that are more or less vertical. These are very local things, and they're broadband, moderately broadband. This one doesn't quite reach the top, and this other one doesn't fully reach the bottom, but they're broadband. But in amongst all these broadband things, they sometimes heard something else. So in amongst all the hissle and noise, you'll have heard a descending whistle, a note that started high and then came down lower and lower. I'll play it again, I hope. It's gone below the... Oh, I can't pick up the icon, it's hidden behind the what's it band? Anyway, pulsar astronomers regularly listen for this kind of whistling descending note, and they regularly make this kind of plot, because these kinds of signals, which are local, would also give a pulse. But because these right and left signals are local, they're not dispersed. All the frequencies arrive at the same time. It's only when a radio wave travels a distance that it gets spread out like this. And the further the distance it travels, the more spread out it gets. So people studying pulsars always make this kind of plot. It's called a waterfall plot. and they look for this descending note. So here's a couple of examples. Here's, for instance, on the right, top right, is a lovely clear pulse, and below its waterfall plot. Starts at high frequency. It follows a slightly curving track as it goes to lower frequencies. Left-hand plot shows a noisier example, but there is a pulse there, and you can see its lovely curvature in its dispersion plot. So this is a sure way of ascertaining that you've picked up a pulse from somewhere distant. So pulsar astronomers on one occasion saw a lovely clean pulse and a lovely clean dispersion curve as it falls lower and lower and lower. The snag is this curve was going down very, 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 very slowly, which means that there were an awful lot of electrons, which are the things that do the damage. There were an awful lot of electrons between the source and us. In fact, so many electrons that they couldn't all be provided by the galaxy. This had to be from beyond the galaxy. And up till then, no pulse had been detected from beyond the galaxy. So it's extragalactic because it's highly dispersed. It was also from sorry, I'm having a lot of trouble tonight. It was also from a spot where there had been no previous pulses of any sort, and there was no optical object there or no X-ray there. And when they worked out the total number of electrons, yep, they really agreed it had to be extragalactic. For a long time, it remained the only pulse like this and therefore considerable puzzle. But the signal to noise is very, very strong. And then they began to find others. So here are a number of them. They're all moderately clear, standing up above the noise. They've become known as fast radio bursts, FRBs, and then they give the date on which they were detected. So this is the 11th of February, 2020, and so on. And they're short, they're bright. They put out more energy than the sun does in a week. We've now seen over 3,000 of these. A handful of them repeat, but mostly they don't. And the amount of dispersion, that curvature, means they're extragalactic. They're typically at redshifts of 0.5 to 1. And there was a big question, and to some extent there still is a big question, what are they? What's causing this? What's going on? Radio telescopes all around the world were looking for these. The Parkes radio telescope picked up some of these and also picked up something else that didn't really make sense. Oh, sorry, that slide shouldn't be there. This is the Parkes radio telescope, and it was picking up some other bursts. Now, Parkes is in Australia. It's in a very remote part of Australia. There are lots of kangaroos, making driving at night difficult, but otherwise there isn't a lot of life. And Parkes has a small building as a residence for visiting astronomers, which is about half a mile away, or a kilometre or two. And they couldn't make sense of these other kind of pulses they were getting until a graduate student, bless them, made a plot of how these pulses fell with local time, with time of day, not astronomical time. And you can see there's a peak around about the middle of the day. What do we all do in the middle of the day? We have lunch. And some of us use a microwave oven to heat our lunch. There's a microwave oven in the residence, a kilometre away. They wouldn't have a Sorry, everything's behaving rather badly tonight. I'm in a bad way. They wouldn't have a microwave on site, but they had one in the residence. And they had actually tested the microwave. They knew it did not leak microwaves. But then they had an idea. And mobile phones are normally banned on site, but one astronomer in the control tower with a mobile phone, another astronomer in the residence with a mobile phone, and a long stick. And they'd set the microwave going, and then the guy in the residence with the long stick would open the microwave without turning it off. And the guy in the control room with the telescope would say, "Yep, there's a burst. You better do it again." So they shut the microwave, set it going, opened it with a broom. "Yep, there's a burst." It turns out that if you open a microwave oven without stopping it, it takes a fraction of a second to stop. So you get a chest full of microwaves in that fraction of a second. Probably not too dangerous, but probably not healthy either. Microwave ovens do not switch off the moment you open the door. They keep going for another microsecond or so. So I recommend, certainly I now always turn my microwave oven off with the button before I open the door. So having solved what these rather peculiar Australian special bursts were, that they were their local microwave, we could then get on with solving a bit more of the science. So many bursts have been seen, by now about 3,000. And they all have this very high dispersion. That dispersion curve drops very, very slowly, which means the sources are way beyond our galaxy at redshifts of about 0.5 or 1. Few seem to repeat, yep, and we're still trying to work out what they are. In Canada, the CHIME telescope, this is it here, distance, this is it rather closer up. It's 4 cylindrical troughs with the antennae, a linear antennae along like this. And it has been picking up bursts very successfully, and it's recently published a catalogue of over 1,000 of these fast radio bursts. It cannot position them very well, but the Australian telescopes have been rather good at positioning fast radio bursts, and this slide shows some of them. So for instance, in the bottom left, it's there, a bit off from the centre. In this one, it's vaguely round the centre. I think this one's also vaguely round the centre. And you can see rather better the error circle in that one. So these things seem to be coming from something in galaxies. There are 24 repeaters so far seen, 612 total, I believe, and about 20 galaxies like this have been identified. But we still don't really know what it is. It's something in a galaxy. Big deal. That doesn't help us a lot. One chime. What's happening? I'm going backwards. Right. Okay. One of the things that interests cosmologists are what are called the missing baryons. Studies of the cosmic microwave background with things like the Planck satellite showed us that particles they call baryons, roughly speaking atoms, make up about almost 5% of the total mass energy of the universe. The snag is we're only getting about 2.5% of that 4.8% in stars and galaxies. So only about half of this stuff we know is in stars and galaxies. And the other half of, must be fairly normal matter, is still missing. Now, through the studies of dispersion of fast radio bursts, in particular where a fast radio burst is seen through another galaxy, we can say very firmly that these missing baryons are in the space between the galaxies. So this has become a very exciting and a very hot topic with lots of interesting results and probably also some useful results. The missing baryons was a particularly good one. a very significant result. Don't quite know where this is going to go next. We are collecting bursts rapidly. Maybe one a day is pretty good going. Not quite sure what happens next, but it's an area to watch. Fast radio bursts. Watch it. Thank you.
Thank you very much for a very interesting talk. And we have some questions from the audience. So you mentioned that the only life around the telescope was some kangaroos. So I wanted to ask, what could be the cumulative effect of kangaroos running around on the observations?
I doubt that's a problem, but of course, as they jump, they provide quite a thump. But telescopes are built to resist even smallish earthquakes. They're quite well padded, so to speak. So I think the kangaroos would have to jump in unison to be its effect. And generally speaking, kangaroos don't do much in unison.
Do we know how large the sources of these fast radio bursts have to be?
They must be less than a light second, because the pulses are under a second long, some of them. So maybe even shorter than that, but less than a light second, that's for sure.
Could fast radio bursts be closer but in dense regions so that they become dispersed?
They could if we had only a few of them. And we also really know quite well what the dense regions in our own galaxy are. So we would be suspicious if they were behind those dense regions. But we've now got so many from all over the sky that there must be a lot of dense regions in the sky.
Are there any that have been detected closer?
I don't think so. Not as far as I know.
How do you see the future of fast radio burst detections and research around radio transients go in the next few years?
Certainly radio transients in general, well, even transients in general, is a very important field. And it's a field where there's going to be more equipment opening up. In Chile, there is the massive Vera Rubin telescope, which will come online in a few years. It's particularly designed to study time domain things that rise or fall in strength on quite a short time scale. And depending who you believe, it will either see 1 million or 10 million such things per night. This means the data cannot be analyzed by humans. It's going to have to be done by computers. And of course, it's going to be crucially important what kind of stuff that the computers will accept and what kind of stuff they will reject. And that's going to be quite interesting of itself. But the Vera Rubin telescope will obviously, I think, reveal a lot more of what we already know about, a lot more that we don't know about. And if anybody's moving into research in astronomy, I would recommend going that way, because it's going to be very exciting and huge fun for the next few years.
What would be the chances of catching a fast radio burst with a big amateur dish? For example, the 9-meter dish of Grotter Weber. I
think probably the dish aperture is only one of the factors. The other is the receiving equipment set up to have very, very short integration time, something like 1/10 of a second. Normally, when you're using a fairly small dish like that, you sit and stare at a source. It's a bit like taking a long exposure with a camera. You have a long exposure, and everything that happens in that exposure is all mushed together and averaged out. So the limitation might not actually be the size of the dish. It might be the receiving equipment.
What do you think about the inclusion of minorities and women in science, particularly astronomy, over the last few decades?
It's getting better, but it's still got some way to go. I keep an eye on the data of the International Astronomical Union, which is for professional astronomers. And women are still very much in a minority. I don't know about other minorities. The data is only collected under two headings, male or female, which these days aren't adequate, but that's what it's been historically. But in terms of gender balance, women are still in a minority, although since they've introduced a more junior membership, then the fraction of females is much higher at the younger age groups, which is encouraging.
Could you live near a pulsar?
Not somewhere where the pulses shone on you, where the beam shone on you. The beam's fairly narrow. You could live well away from where the beam crosses and be okay, but no, not in the beam. And I'd like a very reliable spaceship because the gravity's very strong and I would not like to get pulled in.
Do you think that first pulsar would have been detected if the data reduction would have been done only by computers?
Yeah, that's something that worries me quite a bit. I think probably not, to be honest, because we would not have programmed computers to look for these things. We had no idea such short duration things existed. It was a whole opening up of time domain. And I don't see why we would have programmed the computer to look for such short time resolution. The particular project that I was doing didn't totally require it. At least, sorry, it's a bit complicated to explain. It needed to be recorded at quite high time resolution, but then having got that, you could very quickly average it. And we would probably average it in a computer. So, but at that time, the University of Cambridge had one computer. It took up a whole room. It was made with vacuum tubes, not transistors, and it had memory comparable to your laptop. It was a very early computer.
Thank you again very much, Jocelyn, for this, for your time, for the great presentation, for answering so many questions.